This video is going to talk about the experimental measurement of heat changes and enthalpy changes, and that field is known as calorimetry, named after the calorie, which is 1 unit of heat, although we will use the joule in most cases. Alright, so how do we measure heat changes? Well, basically, the basic idea is that we need to confine our system. And we also want to confine a portion of the surroundings and then call that all of the surroundings, basically. And we confine them by putting them in an insulating container. So if we confine the system and surroundings in an insulating container, if the container is insulating enough, then we can say that the surroundings outside the container can be neglected. All right, and then there are two basic categories of calorimeter, and the calorimeter itself is the insulating container. So one of them I'm going to simply call a coffee cup calorimeter. Okay, and the reason for that is that it's often made out of a simple styrofoam cup. And the other one is known as a bomb calorimeter. All right, first the coffee cup calorimeter. You have some type of a system that you're trying to determine the heat change for, and I'm using a block to represent the system. Now that system in reality might be a reaction, it might be a hot piece of material, but I'm just representing it as a block for now. We put that system in some water. Okay, so I'll make some water. And that way we can see how the water temperature changes when the system does what it's going to do. All right, the other parts that we're going to need are something to stir up the water to keep the temperature similar throughout the water. So we put a stirrer in there to stir it up. And finally, we need to be able to measure changes in temperature, so we have a thermometer. All right, so now if the system, let's say the system was hot, and the system gave off heat, then the water temperature would go up, which we'd measure by the thermometer, all the while stirring it. And we often also put a lid on top of the calorimeter because we don't want the heat to escape through the top either. So in this case, the system, as you can see, is immersed in water. And you can also see that it has a lid on it, but the lid won't be tight. So it's allowing pressure changes to be dispersed with the atmosphere. So basically it is a constant pressure system because it's in connection with the atmosphere. All right, now let's contrast that to the bomb calorimeter. It has many of the same parts. All right, but your system, again represented by this block, is now has two things that it's in. It's inside an inner container which just has air in it, and then outside of that container is where you have your water. So that if the system, let's say again it gave off heat, it would transfer that heat to the air, and then the air is in contact with the water, so the water temperature will still rise, but it won't be directly in contact with the system. And again, you're going to need a stirrer so that the water temperature is the same throughout, and you also, of course, need a thermometer to measure the temperature of the water and what changes it makes. All right, so the difference is that the bomb calorimeter has this thing inside, this inner container, and that is actually the bomb. And it's sealed. That is a sealed container to keep the water from getting into it. Okay, so it's a sealed, dry container. for the system, even though that system is inside some water. And because that container is sealed, the volume can't change. So you have a constant volume system. So in the coffee cup calorimeter, you had a constant pressure system, and in the bomb calorimeter, you have a constant volume system. So for instance, if your system happened to produce gas, the pressure would go up in that container, but the volume would be constant. All right, since the coffee cup calorimeter is a constant pressure, that means that Q, the heat, will be equal to the enthalpy change. You can't say the same for the bomb calorimeter, however. All right, what's true for both of these? In both cases, your surroundings are limited to water and the apparatus. All right, so in both cases, you're not considering the surroundings outside of the calorimeter. You're saying that any temperature changes that occur within the calorimeter are the only ones we're going to take into account. The others will be neglected. And in both cases, you're going to measure the change in the system by measuring the temperature of the water and how it changes. So you're going to measure the change in the water temperature, which is delta T, and that will be produced by any changes in the system. Okay, now let's see if we can apply what we know about the two types of calorimeter to a measurement of enthalpy changes or heat changes in two reactions. So there's two reactions shown here, numbers 1 and 2, and try to figure out which one would be done better in each calorimeter. Okay, so what you have to remember about the calorimeters is that in one case the system is immersed in water and the other one it is not. So the second reaction is an aqueous reaction, aqueous reactants forming water and sodium chloride, aqueous, and that could easily be done in a coffee cup calorimeter. So that one would be a coffee cup. Which is a constant pressure system. The first reaction is all gases. It would be hard to do a gas phase reaction underwater, so that one would be better done in a bomb calorimeter. Before we deal with actual reactions in calorimeters, we're going to look at more simple systems, such as hot rocks or cold rocks or hot pieces of metal, things like that. But why water? Why do we use water in a calorimeter? Because we always use water. And of course there's a couple of sort of obvious reasons. One is that it's very plentiful and cheap and safe. But another reason that we use it is because it has a very high specific heat. So we're going to talk about what that means next. I've written down a few different substances and their specific heat values, which is given by a capital S, and the units are joules per gram per Kelvin. So it's essentially how many joules can the substance hold for each gram of that substance and for each degree of temperature, or each Kelvin. And notice that on this list, water is the highest one, 4.184, and that number we will be using a lot. Iron and lead, both metals, are quite a bit lower, and rubber is about half, and sand is also lower. So water does have a fairly high specific heat. All right, and the specific heat then is a physical property of a substance. And it basically tells you how much heat can it hold. How much heat can that substance hold? So for the larger the S is, then that means it takes more heat to raise some amount of that substance to a higher temperature. So if you take a certain amount, that says temp, if you take a certain amount of that substance and try to raise it to a certain temperature, it's going to take more heat if the specific heat is larger. It also means that if you have a larger S, larger specific heat, that more heat is available from that hot substance. So essentially think of it like a heat reservoir, and the higher the number, the more it can hold. All right, so let's use that information to make some specific heat predictions. And we're first going to look at the system on the left. Okay, so the system on the right and the left are separate. So let's pretend that we have a oven. Okay, this block is an oven at 80 degrees C, and we have a piece of iron in there and a piece of aluminum in there, both of the same mass. Let's say they're the same mass. And we have this specific heat listed for iron and for aluminum. So iron is 0.46, and the units are joules per gram Kelvin, and aluminum is 0.9, so about twice as much. Now let's say, so they're sitting in that oven, we leave them there long enough until the iron and the aluminum are both at 80 degrees, and then we drop them down each into a container of water that is at 70 degrees. And let them equilibrate. So they're both at 80 degrees, so they will both heat up that water. But the question is, after they have finished heating it as much as they're going to, which one of them will be hotter? All right, and it's because of this specific heat that we know that the aluminum one will be hotter. Okay, so this one will be hotter because it has a higher number, meaning it can store more heat in it. Okay, so we can say that aluminum will be hotter because it has a higher specific heat. All right, then let's do a similar but different experiment. Let's say we still have a bin of water that's at 70 degrees, and now we're putting the iron and aluminum in two separate ovens. So we're heating up the iron to 80 degrees C. We're heating up the aluminum to 60 degrees C. All right, so if we just put the iron in the water, it should raise the temperature. And if we just put the aluminum in the water, it should lower the temperature from 70 down to something lower. But the question is, which one's going to win? The iron heats it up, the aluminum cools it down. When the temperature finally stops changing, what will the final temperature be? Will it be equal to 70 because we put in something hotter and something colder? Will it be less than 70, or will it be greater than 70? All right, so again, you have to know the values of the specific heat for the two. We know aluminum is about 0.90 and iron is 0.46. So aluminum has a higher heat capacity, so it will be able to absorb more of the heat, which means that it will change the temperature of the water more. Okay, so since it's changing the temperature of the water more than the iron, and again, we assume they have equal masses of iron and aluminum, it will be closer to 60 than it is to 80. The one with larger specific heat will affect it more, so the answer is it will be less than 70. Okay, because the aluminum will absorb more heat because it has a higher specific heat than iron gives off. The iron gives off heat, the aluminum absorbs heat, but the aluminum has a higher specific heat. So now we're going to switch gears and talk about quantitative calculations that we can do on heat rather than just qualitative arguments of what gets hotter and what doesn't. So for that, we're going to need to figure out how we get heat from delta T. When we do experimental measurements, we measure a change in temperature, but that's not the same as the heat, which is the energy. But they are related through this equation, where Q, the heat, equals S, the specific heat, times M times delta T. Okay, so Q is the heat, S is your heat capacity for a substance, M is the mass of that substance, and delta T is the change in temperature of that substance. So let's do a really simple calculation where we use a calorimeter, like a coffee cup calorimeter, and let's say that our system is going to be something very simple. We're going to make it a hot rock. Okay, remember systems can be reactions. We'll do that in a few minutes. They can be hot metal, they can be lots of things, as long as they are something that changes their heat, or changes their temperature. All right, so we're going to say that the water temperature initially is at 50 degrees C, and it goes to 70 degrees C as a result of putting the hot rock in. So we start with water in this container. It's 50 degrees C. We put the hot rock in. When it's done changing temperature, it's 70 degrees C. All right, and let's further say that we have 100 grams of water. So now let's do some calculations. First of all, temperature, we can write what those temperatures are in kelvins. 50 is 323 kelvins, and 70 is 343 kelvins. All right, so first we're going to use this equation to figure out how much heat the water gained. Okay, so the heat for the water is going to be equal to the specific heat of the water times the mass of the water times the change in temperature for the water. All right, the specific heat for water we get from that chart, 4.184 joules per gram Kelvin, and the mass of our water is 100 grams, and delta T is the final temperature minus the initial temperature, which is 343 minus 323 Kelvin. And so we can solve for that, and we get 8,400 joules. I'm not going to worry about sig figs for the moment. All right, so that's how much heat the water gained. But how much, if we are interested in the rock, we want to know how much heat the rock lost. Okay, well, if we're assuming this container is completely insulated, then the amount of heat that the water gained is the same as the amount of heat that the rock lost. Okay, so we can say that Q for the system, which is our rock, is opposite sign, negative, for the Q for the water. Okay, so in other words, if the water heated up, then the rock must have cooled down. That's why we have a negative there. So we can simply say the heat for the rock is negative 8,400 joules. Okay, so obviously we are assuming in this case that all the heat from the system went from the rock to the water. It was completely insulating. All right, so again, just to repeat, the crucial part is to realize that the heat for our system, whatever it may be, is the opposite sign for the heat for the water. If we put a hot rock in, the water heats up, the rock cools down. If we put a cold rock in, the rock heats up and the water cools down, but they always will have opposite signs. Another thing that you may note is that we actually didn't need to convert to kelvins because we are doing a change in temperature. If it's a delta T in kelvins is equal to delta T in degrees C. So in other words, in kelvins it was 343 minus 323, but in degrees C it would have been 70 minus 50. So in both cases it's just 20. So as long as you're doing a delta T, you don't actually have to convert to Kelvin. Now that we've done the calculation for a simple system, which is a rock, let's make it a little more complex and a little more useful by using a reaction for the system. Okay, and this is going to be a generic reaction where I have A plus 2B going to C plus 2D, and we want to know the delta H for the reaction. So the setup is that we have 17 grams of A, and there's the molar mass, reacted with excess B in a coffee cup calorimeter containing 100 grams of water. The temperature of the water increased to 20 degrees C. Find delta H. Alright, so one of the first things that we know from before is that the Q for the system is going to equal minus the Q for the water. Okay, but in this case the system is a reaction. So the Q for the reaction, the heat of the reaction, is going to be the opposite for the heat of the water. All we have to do is calculate the heat for the water, change the sign, and we will have the Q for the reaction. So let's do that. Okay, so our system has been put in 100 grams of water, and so the Q for the reaction is going to be minus the Q for the water, so I'm going to put the minus in there right away, and I'm going to say that's S for the water, M for the water, and delta T for the water. Alright, so let's put in our numbers. We know that S for water is 4.184. That's a constant for water. The mass of the water here is 100 grams, just like last time. And the delta T, it's telling us the delta T. The water temperature increased 20. We don't even have to calculate delta T. It's given to us. So that's 20, and that's C or Kelvin. The delta T is the same. All right, so that gives us, so we can do that calculation, and it turns out it's the same number as I did last time because I'm using the same change in temperature and the same amount of water. So let's say the reaction did the same thing as the rock, and we get 8,400 joules. Then the Q for the water is 8,400, so the reaction is negative 8,400 joules, which means that it's an exothermic reaction, right? Because the Q is negative. Okay, and that makes sense. If the water temperature increased, that means the reaction produced the heat that increased the temperature of the water. All right, but is that delta H? For the reaction. Okay, so we used some amount of A and reacted it and got some amount of heat, but what if we used twice as much A and or different numbers? So basically we never used the fact that we had 17 grams of A, which means that we haven't actually found out the heat for the general reaction. Remember, the heat for the general reaction is for 1 mole of A and 2 moles of B, forming 1 mole of C and 2 moles of D. We didn't have 1 mole of A, we had 17 grams of A. So to find out the actual delta H for the reaction, we have to figure out what this heat would be if it were for 1 mole of A. Alright, so that's not a difficult calculation, but you have to realize the Q for the reaction is for the amounts we used, not for the equation as it was written. Alright, so our delta H is going to equal that heat, and then we just have to divide by the number of moles we used. Okay, how many moles do we use? Well, we have to start with the grams and convert it to moles. And the molar mass of A was given, 42. Okay, so basically I took the heat we had, I'm dividing it by the number of moles. I did this whole denominator is a calculation of the moles. So we're just dividing the Q by the number of moles. We'll still have a negative sign, and it'll be negative 2,100 joules that now we have per mole of A. So that's a number that is more universal. It's actually for the equation up above. So we can now say delta H is negative 2100 joules. Okay, so this was an exothermic reaction. Q and delta H for the reaction were negative. What would be different if this were an endothermic reaction? Well, if it's an endothermic reaction, that means the system absorbs heat, which means the water loses heat. So delta T for the water would then be negative. And therefore, the Q for the water would be negative. And therefore, the Q for the reaction, which is the opposite sign, would be positive.